Hello everyone. I'm glad you're here. Before we dive in, think about lifting a heavy suitcase into a car versus rolling it up a short ramp. Same job, but one feels much easier. That's the magic of a machine. A machine is any device that helps us do work more effectively by multiplying the force we apply, changing its direction, or trading force for speed or distance to suit the task. In physics terms, we put in work as effort times distance moved by effort, and we get out useful work as load times distance moved by load. Because of energy losses, the output is always less than or equal to the input. No machine creates energy from nowhere. This is why we say the principle of a machine respects energy conservation. In real life, some of our input goes into friction at pivots and axles, bending of ropes or chains, deformation of parts, and even sound and heat.
Mechanical advantage is defined as the load divided by the effort. It indicates how much the machine multiplies the applied force. If the mechanical advantage is greater than 1, it means less effort is required to lift the same load. The velocity ratio is the distance moved by the effort divided by the distance moved by the load. It is a geometric or kinematic quantity and, in the ideal case, is independent of friction. Efficiency is calculated as work output divided by work input multiplied by 100%. It can also be expressed as mechanical advantage divided by velocity ratio multiplied by 100%. Efficiency compares the actual force gain to the ideal kinematic gain. In an ideal frictionless machine, efficiency is 100% and the mechanical advantage equals the velocity ratio. In real machines, efficiency is always less than 100%, meaning the mechanical advantage is less than the velocity ratio for the same geometry. For example, if the mechanical advantage is 4 and the velocity ratio is 5, the efficiency is 4 divided by 5, multiplied by 100%, which equals 80%. The remaining 20% represents the energy lost due to factors such as friction.
The law of the lever states that for a lever to be in equilibrium about its fulcrum, the torque produced by the effort must equal the torque produced by the load. This can be expressed as effort multiplied by the effort arm equals load multiplied by the load arm, representing the condition for torque balance. Levers are classified into three types based on the relative positions of the fulcrum, effort, and load. In a Class 1 lever, the fulcrum lies between the effort and the load. In a Class 2 lever, the load is positioned between the fulcrum and the effort. In a Class 3 lever, the effort is applied between the fulcrum and the load. This arrangement determines whether the lever is designed for a force gain or a speed gain. The ideal mechanical advantage of a lever can be determined from geometry as the ratio of the length of the effort arm to the length of the load arm. A longer effort arm produces a greater mechanical advantage, which is a common feature of Class 2 levers. In some cases, levers trade force gain for speed. Class 3 levers often have a mechanical advantage less than 1, meaning they require more force than the load's weight, but they provide greater speed and a larger range of motion. This makes them especially useful in human limbs and certain tools where quick movement is more important than maximizing force. In a single fixed pulley, the pulley changes only the direction of the effort and does not provide any force gain. The velocity ratio in this case is 1, which means the ideal mechanical advantage is also 1. In practice, the actual mechanical advantage is slightly less than 1 because of friction at the axle. In a single movable pulley, the load is supported by 2 strands of rope. This arrangement gives a velocity ratio of 2, which means the ideal mechanical advantage is 2. As a result, the effort required is ideally half the load. A block and tackle system combines fixed and movable pulleys. In this arrangement, the ideal velocity ratio is equal to the number of strands that directly support the load. However, when more pulleys are added, the friction in the bearings and at the bends in the rope increases. This means the actual mechanical advantage is equal to the efficiency multiplied by the velocity ratio, with efficiency generally decreasing as the system becomes more complex. Think back to that suitcase and the ramp. That's an inclined plane. Ideally, the velocity ratio is L over h, spoken as length of the plane divided by the vertical rise. With friction present, say the coefficient is nu, the required effort exceeds weight times h by L, and the efficiency drops below the ideal. The wheel and axle works on the same torque idea. VR equals capital R over small r, where capital R is the radius of the wheel and small r is the radius of the axle. A larger wheel radius compared to the axle radius multiplies torque, letting a smaller effort raise a larger load. A screw or screw jack is essentially an inclined plane wrapped in a helix. For each full turn, the effort point travels a circumference of 2 pi r, while the load rises by the pitch p. So the ideal velocity ratio per turn is 2 pi r divided by p. Due to thread friction, efficiency is reduced, but that same friction can be a safety feature. Many screws are self-locking, meaning the load will not drive the screw backward if you let go. As you can see in the diagram, mark L and H on the ramp, R and R on the wheel and axle, and P, the pitch, along the screw's axis. Engineers often summarize a real machine's behavior with a simple linear model, E equals ml plus C. Here E is the effort, L is the load, m is the slope telling us how quickly the needed effort rises with load, and C is a constant effort that represents frictional resistance even at tiny loads. Ideally, we would expect m to be close to 1 by VR, but friction changes that. To determine these numbers, we measure the steady effort required for several loads, then plot E on the vertical axis versus L on the horizontal axis. As you can see in the graph, the straight line slope is m and its intercept on the effort axis is c. Once we have m and c, we can predict the effort for any desired load, compute the actual mechanical advantage as ma equals L divided by E, and then find the efficiency for that load using eta equals ma over VR times 100%. This experimental approach turns a real, imperfect device into a predictable tool. We are given that the screw jack has a pitch of 5.0 mm or 0.005 meters and a handle radius of 0.40 meters. The load to be lifted is 12,000 newtons and the measured effort required for this load is 250 newtons. When the load is close to zero, the effort required is 40 newtons. From the ideal kinematic analysis, the velocity ratio in the frictionless case is calculated as 2 pi multiplied by the handle radius divided by the pitch. Substituting the values, we get 2 pi times 0.40 divided by 0.005, which is approximately 502.6. In an ideal, frictionless machine, the mechanical advantage equals this velocity ratio. In actual operation, the mechanical advantage is the load divided by the effort, which is 12,000 divided by 250, giving 48. The efficiency is then the mechanical advantage divided by the velocity ratio multiplied by 100%. This equals 48 divided by 502.6 multiplied by 100, which is about 9.6%. Using the law of the machine, the effort can be expressed as m times the load plus c, where c is the constant effort to overcome friction at no load. Here, c equals 40 newtons. Substituting E equals 250 newtons at a load of 12,000 newtons, we find m equals 250 minus 40 divided by 12,000, which is approximately 0.0175. Therefore, the equation of the machine is E equals 0.0175 times the load plus 40. Let's wrap up. Machines don't give us free energy, they help us apply force and motion in smarter ways. we learn to quantify performance with three measures: MA equals load over effort, VR equals effort distance over load distance, and eta equals MA over VR times 100%. In ideal cases, MA equals VR and efficiency is 100%. In real devices, friction reduces both. Levers, pulleys, inclined planes, wheel and axle systems, and screw jacks all follow clean geometric relations that guide both analysis and design. The linear relation E equals ml plus C captures real-world friction and lets us predict performance from experiments. So to sum up, the physics of machines explains everything from opening a door to raising a car on a jack, and from simple school lab setups to industrial lifting rigs. I hope you now have a clear, intuitive feel for how machines trade force and distance to make work easier. See you in the next session with another fascinating concept of physics.